Ants, one of the most fascinating and mystical creatures on the planet. Though they may not appear to be much alone, together one colony of ants becomes a one brain, united by a system of neurons. Each ant plays the role of one brain cell, sending messages back and forth with complex chemical signals known as pheromones. Ants are in fact one of the most efficient and intelligent beings on the planet. Ants, much like humans, build complex communities and structures, create stockpile, and are even known to farm. Ants are all interconnected through a complex web of interactions, driven on an entirely chemical basis. Over millennia, ants and their pheromones have evolved to serve the ecosystems in which they reside. All this and more we have discovered on our quest to find the chemistry of ants. If you have ever been out on a bright sunny day, it is likely you have come across some type of ants going about their daily business. You may have seen them foraging around for food or building a nest. You may have even seen them locked in combat or invading an enemy. Collectively, ants are one of the most highly organized and cooperative organisms in the world. A colony works together to transcend the size of each species have very limited eyesight. Many are even blind. This puts them at a large disadvantage when it comes to communicating and coordinating efforts. It is a way they are able to harmonize their efforts toward completing one shared goal. How do they do it? The answer is pheromones. Pheromones are chemical substances that animals use to communicate with others of their own kind. Pheromone use is very common among various insect species, but it is not limited to insects. Cats, deer, and mice are among the many animals that communicate through pheromones. Pheromones are known to serve many different purposes, including those of finding food, marking territory, and differentiating between other species members and intruders. In the case of ants, pheromones serve all of these purposes and more. Due to their lack of other senses, ants are heavily reliant on their pheromones.
Our goal in this demonstration was to show just how dependent ants are on pheromones to getting around. And what we did is we basically looked for ants that were staying true to a trail that they had established or had been established. And we basically just smudged the trail with a finger and watched how the ants reacted. In all these cases, they just sort of stopped and tried to regain their bearings, but they were pretty lost without their trails. In this case, the ant was carrying some food to its nest, and then it drops the food, and then it just starts running around, not really knowing where to go.
Lay a trail of pheromones as they walk. When foraging for food, for example, ants will leave their nest and venture out. In this case, their trail serves two purposes. The first is to lead the ant back to its nest. If an ant does in fact find food, it will travel back to its nest to signify others. Other ants will then follow the same trail and proceed to collect the food. The more ants use a trail, the hotter and stronger it gets. If another worker comes across a very used trail, it too will follow it to join in on the work. Conversely, an ant is less likely to follow a weak trail that is further along in the evaporation process. In general, ants are very sensitive to their own pheromones. In fact, just 1 milligram of pheromone would lead a whole ant colony 3 times around the world. Ants use trail unique. For example, the Atta texana, which lives in dry, sandy soil in and around Texas, has the trail pheromone C7H9NO2. This chemical, called methyl-4-methylpyrrole 2-carboxylate, is polar, giving increased vaporization point. This is an advantage when it comes to its use as a pheromone, as it takes longer for a trail to evaporate and lose its scent. Under the hot Texan sun, this is very important. On the other hand, the polarity of this pheromone makes trails soluble in water. However, rain and wet climates are uncommon in the Atta texana's habitat, making the trails dissolving in water a non-issue. However, the Myrmica rubra, which lives on the coast of Maine, uses the non-polar pheromone 3-ethyl-2,5-dimethylpyrazine with the chemical formula C8H12N2. The fact that this pheromone is non-polar protects it from being washed away by Maine's damp climate. The disadvantage is that it has a lower vaporization temperature than methyl-4-methylpyrrole 2-carboxylate. But due to Maine's more moderate climate, this becomes a relatively insignificant issue. Yet the chemical world of ants is not all chatting and snacking. If you look closer, you'll find a constant state of war. Here one colony of ants charges upon another, aiming to eliminate the other and dominate terrain for the promise of food found within. If ants were humans, their war would not be that of the primal ages. No simplistic barrage of clubs and spears. Instead, it would be that of the future. Troops with specialized chemical weapons, aiming to exploit and obliterate their opponents. Found all across the Eastern Hemisphere, the Formicinae family of ants appear physically similar to most ants, but they have a special attribute not seen across many other species: venom glands that produce formic acid. Formic acid is the most basic of the carboxylic acids, the series of acids with varying R group connected to its acidic component, a carboxyl group with the chemical formula COOH. Whereas the more complicated carboxyl acids are often found within different foods, the two smallest, formic and acetic acid, are indeed quite intimidating. Formic acid, HCOOH, may be a weak acid, but it can still prove quite dangerous. With a Ka of 1.77 times 10 to the minus 4 and a pKa of 3.75, it serves as a vital weapon for Formicinae ants. In fact, it is a stronger acid than the often used acetic acid. Here one can observe an onslaught of two Formicine colonies, one upon another. In an attempt to overpower the others, the ants spray formic acid from a gland in their abdomen, thus damaging, stunning, and possibly killing the ants. Formic acid is not an ant's only weapon, however. Often in the deserts and hotter southern areas of America, fire ants can be found. The name of these ants does not arise from their burgundy colour, but instead from the burning sting which they are capable of delivering. The ant carries venom sacs connected to a stinger on their abdomen, allowing them to inject toxin into their victims. The venom of the fire ant is comprised of piperidine alkaloids. These are nitrogenous natural molecules in which the piperidine compound can be found. Piperidine is a hex-ringed shaped structure. The most significant piperidine alkaloid contributing to the painful effect of the fire ant bites is solenopsin. Essentially a piperidine with a long hydrocarbon tail, solenopsin has the chemical formula C17H35N. When introduced to an organism, it binds with a surface cell enzyme known as P13K. By binding to the enzyme, solenopsin prevents it from carrying out one of its primary functions, angiogenesis, the growth of new blood vessels. Effectively, the introduction of solenopsin through a fire ant damages the cells at the point of stinging and then isolates them from receiving assistance by inhibiting blood vessel growth. One final interesting element of the formic defence system concerns the seemingly confusing characteristic of certain Malaysian species to cause themselves to explode, inducing immediate death. When Campanensis saundersi feels threatened in combat, either with ants of another colony or with different insects, it initiates autothysis, self-explosion. The ant contracts its abdomen to erupt along a seam reaching from its gaster to its head. Included in this explosion are the ant's two enlarged mandibular glands. When eruption occurs, a secretion is released in all directions with the aim of covering enemy insects. This secretion serves as a glue sticking the enemy insects to any nearby surfaces, thereby letting fellow colony members either flee or attack the immobilized opponents. The sticky fluid is composed of a series of hydroxyacetophenones, specifically two isomers, 2 and 4 hydroxyacetophenones. These two molecules are composed of a hydroxyl group bonded to an acetophenone. In turn, acetophenone is an organic base compound composed of a hydrocarbon hex ring bonded to an acetyl group. These three components combine to create a final chemical formula of HOC6H4COCH3. These are just a few of the ways ants utilize chemicals. As we've shown, ants are able to communicate, fight, and defend themselves due to the chemicals they use. Ants, being one of the most advanced and evolved organisms on the planet, are perfect examples of the significance of chemistry. It is important, when looking down at the ground at these tiny chemists, that we look up to the future and decide on what role chemistry will play in shaping our world. Here one can observe an onslaught of two formicine colonies, Here one can observe an onslaught of two formicine colonies, one upon another.